Good morning, y'all. The first thing I want to do is so I'm planning for the same format as last time. If there's any protests, if you can't get here by 9, or have to leave before 10, let me know, and I can change that. I don't want to run it from 9 to 10. Remember, you have to get it uploaded, give you a 5-minute grace period to upload it to Canvas. So, bring a paper and the exam will be on campus kind of thing. Got to take pictures and upload it. Review. I suppose you all would look at a review section, perhaps. I think that, just so I can get things posted up and, so I can deal with lots of questions, Wednesday would probably be more optimal. Session, let's say can anybody not make that time? I would, I'm sorry it's so late, but I actually have a meeting from 2 o'clock till 7 o'clock on Wednesday. 7, all right with y'all folks? Let me stick around and see what I can come up with as far as the classroom. I'll update. And by Wednesday, I mean, of course, a week from today. Okay, any questions from last time? Okay, so let me well, actually, before I do that, let me stick something else. Here's the big sort of classic examples that I want you guys to kind of focus on, because it turns out that I want to only do this for finite groups, but any finite group is a subgroup of one of these things. So if you've got any finite group in the world, then it lives inside of one of these symmetric groups. And this is actually true in the infinite case as well, but I'm going to focus on that too much. So okay, so just let X be the set of the first n numbers, right? N could be 10, n could be 1, that would be boring. And we actually did this last time for n equals 3, but Sn equals the set of F. That's that F in the bijective. Right. So for example, let's see, let's come up with a bijective function in S6. Well, 1 could go to 3, 2 could go to itself, 3 could go to 4, 4 could go to 1, 5 could go to 6, 6 goes to 5. This function is bijective, right? It's 1 to 1 and on 2. It's a pairing off of things. Sometimes the elements of these are called permutations, because that's really what you've done is you just 1, 2, 3, 4, 5, 6, and you've rearranged them into a new order, right? Everybody okay with that? Now, this will be kind of a good review of groups. Notice we combine F1 and F2 in Sn in function composition. Right? So we've got this function from one to n to itself, this function one to n to itself is bijective. What happens when you compose two bijective functions? You get a brand new bijective function. Everybody agree with that? And so this is why bijection is important, because now this, you've got closure. That is to say, if you combine these two elements of Sn, you get a new element of Sn, a new bijective function. What else do we need to be a group? We need the operation to be associative. Actually, we showed earlier in class, like not last time, earlier in this class, the function composition is always associative. So we got that way. The identity function the function that takes every one of these numbers to itself is the identity. If you compose with the identity function in either direction, it leaves everything alone. And since each F is a bijection, its inverse, F inverse, is a bijection. Is a function and a bijection. And so this is actually a group. Everybody okay with it? And like I said, it's an important group because every finite group is in some appropriate Sn. Now, I taught you all notation last time, and I implemented it for S3, but let's do something a little bit larger. Now, if I were to write the elements of S6 down, how many, by the way, how many elements of Sn are there? How many bijections are there from separating things to itself? Right. So if you think in S6, how many places could I have sent one? Six of them. Once I've made that choice, how many places can I send? 2, 4, 3. So it should be 6 factorial. In general, this is n factorial. There should be n factorial bijections from n elements to itself. Now, S6, therefore, has 720 elements. I do not want to write down 720 simple little functions the way I wrote down here. That's very unwieldy, right? And so I've got a shortcut notation for this function. How does this work? Well, where does 1 go? It goes to 3. Where does 3 go? 2. Where does 2 go? To 1. This is called a cyclic notation. This means 1 jumps to 3, 3 goes to 2, and 2 jumps back here. Okay, let's see. How about 4? Where does it go? 4 goes to itself, so I'm going to close it off here. All right. Where does 5 go? 6. And 6 goes to? Better, because it's a bijection. Sometimes people abbreviate this way. Right, because of the 4, but you can leave that there certainly to emphasize the 4 goes to itself. Now, you can write all 720 elements in this so-called cyclic notation. Yes, sorry.
I was about to ask what the notation is called.
Oh, right. This is called cyclic notation. These pieces here are called cycles. And in fact, any element of Sn can be written as a product of disjoint cycles. Notice that these two cycles actually commute with each other. This is the same thing as because this tells the function to do the same thing. It tells 5 to go to 6, 6 to go to 5, 4 is left alone, 1 goes to 3, 3 goes to 2, and 2 goes to 1. It's the same thing. If the cycles overlap, it doesn't make any difference. If the cycles have something in common, so if you just wrote this down, what is this? How do we do the multiplication? Well, we talked about this last time too. I will start with 1, just because it's the first number I see. Go from right to left, like function composition. This is the way it's done. Where does 1 go? It goes to 3, and then 3 is left alone, so 1 ends up at 3. Pick up where you left off. Where does 3 go? It goes to 1, and then back to 2. If I've done this right, 2 better than 1. See what happens. 2 is left alone, goes to 1. Notice this is different. If you do the same multiplication, these are different functions here. But it's only because there's an overlap. Things can go wrong there. Let me do a larger example of how to do this multiplication. And we're going to be using this as a tool. So make sure that you do this. This is an element of S8. Actually, it's an element of S anything 8 or larger, right? Because you could just pretend that this is S9 and 9 is left alone, whatever. Let's go through what happens here. Where does 1 go? All right, let's go through it. Just like function composition. There's my first one. 1 goes to 7. No 7. 7 goes on to 2. It jumps to 8. No 8, no 8, no 8, no 8. So it ends up at 8. Everybody follow that so far? Pick up where you left off. Where does 8 go? No 8, no 8, no 8. Jumps to 2, to 5, to 2. So it ends up at 2.
Does it matter where you start, that comes up to the right?
Yes, it will, because I want us all to be consistent. If you multiply from the other direction, you'll get a different answer. You should always go from right to left. And the reason I force you to do that is because that's what, that's what all the literature does. That's the common convention. And the reason you go from right to left is because it's like function composition. You plug in like that. Now, where are we? We're at 2. Where does it go? It goes to 6. No 6, no 6, no 6, no 6, no 6, no 6, no 6. So there we go. How about 6?
You write it just because it.
Okay. 6 goes to 1, into 2, into 5, back to 2, to 3, to 5. Okay. How about 5? Where does it go? 5, goes to 3, to 2, to 1. So it goes back to 1. Everybody okay with it? Okay. I've used up 5 of my numbers. What's the smallest number that I really haven't accounted for? 3. So let's see what happens to 3. Actually, you can pick up at any number that you haven't covered, but I might as well just do this in a logical fashion so I don't get lost. 3 goes to, no 3, 3 goes to 1, to 4, and it's done. And where does 4 go? It goes to 2, 3, to 7, to 1, to 3. Well, what's the smallest number that I haven't accounted for? What's gotta happen to 7? It better go to itself or I screwed up somehow, but it's always good to see if I'm doing screwed up or not. Let's see what happens to 7. It goes to 4. Back to 7. Okay, so I feel good about myself. Everybody feel like they understand how to do that? These are kind of easy to practice. And of course, you can set this up with like my chart like this and just compose the function, but you'll see that you get the same thing. By the way, well, these examples we could follow. Anybody want to guess what the inverse of that is? That seems logical, doesn't it? And yes, that works. Let's test it, shall we? So to do a cycle, the inverse of a cycle is just running it in the backwards, right? Let's see what happens here. Where does 1 go? 1 goes to 3, back to 1. Where does 2 go? It goes to 1, back to 2. And where does 3 go? It goes to 2, back to 3. So you get the identity function. And everything's looking. Can you generalize? What do you suppose this is?
6/4 times.
Let's run everything in reverse. Now, you might criticize me a little bit because I turned the order around. That's because of the following theorem. And this will look familiar from linear algebra because you saw a similar thing with invertible matrices. The identity of a group is unique. So we know that the group, one of the assumptions about a group is it has an identity. This theorem says there's only one identity. Two, the inverse of any element is unique. So in particular, you know that X and Y have inverses. There's only one inverse for X, and there's only one inverse for Y. Any guesses on that? Why? It's the inverses and the opposite. Just like with matrices. Y'all remember that about an invertible matrix? A times B inverse is B inverse A inverse. Let me show you why this is true. Actually, I won't do the whole thing. Only part of this is an exercise. It's not too difficult, but I'll show you the first one just because it's silly. Suppose E and F both I almost feel like I could take a shower after this. E is F times E because F is an identity. Right? Because since F is an identity, when I multiply F by E, it's E. Agree? of this is F. Because E is an identity. Right, because now think of E as the identity, so it's F, so E and F are the same thing, and there's only one. Right, so any two identities are equal. Okay. For number 3 in my statement, notice that Y inverse X inverse times XY is Y inverse X inverse X times Y, which is Y inverse EY, because X inverse X is the identity, which is Y inverse Y, which is the identity. And let me be super anal about this and check it from the other side. So XY, Y inverse X inverse is X times YY inverse X inverse, which is X E X inverse. So notice that Y inverse X inverse on either side of XY turns it into the identity. This means that Y inverse X inverse is the inverse of XY. And statement 2 says that that's an equality because there's only one inverse. Okay, any questions on this? Okay, I'm going to give you a theorem also. If I arm you, so what are some groups that we have? Well, we have the integers under addition, right? Notice the integers under multiplication is not a group, is it? Anybody explain why? The integers under multiplication, integers under addition, okie dokie. Integers under multiplication, not so much. Not a group. Anybody explain why? Well, let's go through. What happens when you multiply two integers? What do you get? Another integer. So far we're cool, right? Is multiplication of integers associative? Sure it is, right? We wouldn't be doing math if that weren't the case. Is there a magic integer that I can multiply by any integer and it leaves it alone? 1. 3 out of 4. That's better than meatloaf. Now, how about inverses? Now we're talking multiplicative inverses, right? Does 2, the integer 2, does it have a multiplicative inverse? Well, yes, it does. It's 1/2. But is 1/2 an integer? No. So it's multiplicative inverse. In fact, can anybody name what are the only integers that have multiplicative inverses that are integers? -1 and 1. And in fact, you can fix that example because every integer has a multiplicative inverse that is a rational number by expanding this to rationals, with one glaring exception. There's one hombre among the integers that is so bad that it doesn't have an inverse at all, no matter what you do. 0, right? There's no curing 0. The integers under addition, to sort of bolster up that example, the non-zero rational numbers under multiplication is also a group, right? Multiply two rationals, you get a rational. The inverse of A over B is B over A, as long as the numerator of the original wasn't 0. This was a big one, Zn for any n. We talked about that one last time. And 4, Sn, these crazy functions that we had last time. Is that it? Well, no, actually, there are lots and lots of groups. It turns out that for a group of prime order, right? So suppose I want to have a group of order 2. Z2 is one of them. And in a certain sense, that's the only one. Every group has the same, every group of order 2 has the same structure as Z2. We'll talk about that in a moment. However, and in fact, you can say the same thing about any group of prime order. If it's order 3, 5, 7, there's only one group of that order, only one structure you put on it. However, there are 2 groups of order 4. There are 5 groups of order 8. There are 14 groups of order 16. And there's, I believe, 51 groups of order 32. And it starts to spiral out of control very badly. So I'm going to give you a theorem of a way to make some more groups. So I want to write this out. It's a theorem, and the notes is called the definition. But I'm going to stay with this one. On H star the groups. And I write the circle and the star to emphasize that they may have different operations on them, right? Like G might be the integers under addition, and H might be the non-zero rationals under multiplication. They might have different operations here. I can make a new group out of these old ones. So here's the definition part of this theorem. G cross H, which is the set of G, H, with G and G. Notice this is just a set of ordered pairs. First coordinate comes from G, second coordinate comes from H. Is a group with okay, I want you to help me here. I'm going to make a new group. So I've got G with its operation circle and H with its operation star. And I want to create a new group whose elements are now ordered pairs, right? So it's a little bit bigger than G and H. Now, I've got a thinkable way to multiply these two things. And it's got to give me an output that's still in G cross H. So I've got to have a first coordinate in G, and I've got a second coordinate in H, just like this. Now, sometimes math seems a little bit opaque to some people, but here's the rule at the end of the day. In math, if it ain't easy, don't do it, right? What is the easiest way you can think of to take this data and have it barf out a coordinate in G? What's the easiest way to take that information there to get a new coordinate in G? Multiply the G's, absolutely. And how about second coordinate for H? Multiply the H's with their, with H's operation. This is actually a group. What do you suppose the identity of this group is going to be? What's the ordered pair that'll leave everything alone? Well, it's got to have two coordinates, right? It's got to have a G coordinate and an H coordinate. What's your best candidate for something to leave everything alone? What do you want your G coordinate? The identity of G. And what do you want the H coordinate? The identity of H, right? See if you can prove, this sounds like something that might come up on the homework here. See if you can prove that that is a group under these operations, but it's not very difficult to show that. Okay, any questions? How many of you have ever heard the word homomorphism before? I wouldn't be surprised if you haven't, right? That's, but subgroups, I think, subgroup is like a little bit more self-explanatory. What do you suppose a subgroup of a group is? Well, it's just a little baby group inside the group, right? It's a little piece of the group that is still a group. Definition. Let G be a group a subset, which is non-empty, group theorists use this less than or equal to. They sharpen this instead of the thing, instead of using the subset notation, but I'm not going to pick on you too much about that. A subgroup H of G is a non-empty subset H and G such that H is itself. Okay. Okay, so let me start off with the if I have any group in the world I can think of two rather silly examples of subgroups. Anybody think of sort of silly extreme examples of subgroups of G? What's that? You got the hardest part. But to be a subgroup, there's only one choice for what that one item is. Oh, okay. That's one right there. G itself is a subgroup of G, right? Because G is a subset of itself and it's a group by definition. There's also a smaller one. Well, usually small one. That would be a good choice, except for close. There's always a subgroup of one element. Anybody name what that is? The single element, the identity, is a subgroup. Because what happens when you multiply the identity by the identity? It's still the identity, so it's closed, right? Associative is stupid because identity is everywhere. The inverse of the identity is the identity, right? And let's see, what am I forgetting? Associative. Well, and of course, it's got the identity because it is right. So that's an extreme. And of course, these are usually two different examples. In fact, they're distinct unless G itself is the identity, right? Let G be the integers under addition. Okay. Zero is a subgroup of Z. right? It's closed under addition, and all that other silly stuff. And so with Z, can anybody give me any other subgroup of one that's not extreme like these two examples? Can you think of a subset of the integers? In fact, this might help. Can you think of a subset of integers that's closed under addition? That's a good idea, right? Certainly the negatives are closed under addition. The problem is to be a subgroup, everything's got to have its inverses. So once you've got some negatives, you got to have the corresponding positives. Is anybody even going to try?
The evens.
How about the evens, right? What happened? What about all the integers that are multiples of 2? Right? What happens when you add 2 multiples of 2? You get another multiple of 2. Let's see here. Of course, addition is associative. You usually don't have to check that because I know that addition under Z is associative, so it's inherited in any subset. How about the identity 0? That's an even number as well, so that's contained in there, right? And what about the inverse of an even number? And here inverse means additive, right? If you have 2k, its inverse is negative 2k, which is also even. Right? There's another. Everybody convinced that's subgroup? Can you generalize that? In fact, I will parameterize them. I'll list them all. Every subgroup of C of the form in Z, where n is a natural number or 0. So for example, when n is 0, you get 0Z, you get this. When n is 1, you get this. When n is 2, you get this. But you can use any n. All the multiples of 17, that's a subgroup of Z. All the multiples of 300, subgroup of Z. And in fact, these are the only ones. I might ask you to show that later. That sounds like a good homework problem too. And the good thing about this one right here, what's interesting about this is the reason that this is true follows from the Euclidean algorithm. As a matter of fact. So that's another, once again, the properties of the integers step in and assert their importance. Never to be ignored, they are. Okay. How about some other examples? Here are 4 big groups. The rationals under addition, the real numbers under addition, the non-zero rationals under multiplication, and the non-zero real numbers under multiplication. All 4 of those have a truckload of subgroups. In fact, all of these have infinitely many, and in fact, the number of subgroups that this one has is a larger infinity than the number of elements in Q plus, as a matter of fact. Let me point out suppose you have a finite group of order n, then G has G has only finitely many subgroups, right? I know it's got at least one. Well, if I count this as two, then it's got at least two, but if G is the identity, this is only one. So any group has at least one subgroup, at least one subgroup. If there's n elements in G, can somebody give me an upper bound? So I just rather flippantly claim that G has only finitely many subgroups. Can anybody give me a ballpark based on what n is? Well, let me ask you this. Let's just get really not even thinking about the group stuff. First and foremost, G is a set and it's got n things in it. Forget about the group stuff. How many different subsets can G have? How many subsets does a set of n things have? 2 to the n, right? And so the number of subgroups of G is less than or equal to 2 to the n minus 1. Why the minus 1? What did I toss out? I tossed the empty set because I know any subset can't be empty. And actually, even though I tossed the empty set, that doesn't make my bound that much better. This bound is usually grossly too big. The number of subgroups is usually much smaller than this, but that's kind of a worst case scenario. We can never exceed that. Let me give you an example here. Let's get hardcore with the concrete. I'm going to take two groups of order 6. And these groups are different. And I mean different, not only they look different, but they're kind of philosophically different as well. This is a tale of two groups. Here's one of them, Z6. This is a group under addition, the clock addition, so to speak. Can anybody give me a different group of order 6? Maybe one that's not. This one's abelian, right? Order doesn't matter what order I add those things up in, right? Anybody give me an example of a group that's not abelian and of order 6? What do you know about the number 6? How do you factor 6? Right, and let me be more dramatic. How about 3 times 2 times 1? So 6 is actually 3 factorial. Can you now name another group that has 6 elements in it that's not abelian? How about the bijections from 3 elements to itself, right? Let me list the elements of this. These are the 6 elements of, these are the 6 bijective functions, right? This bijective function swaps 1 and 2 and leaves 3 alone. This one swaps 2 and 3 and leaves 1 alone. This takes 1 to 2, 2 to 3, and 3 back to 1. That's everybody okay with that? Notice both of these groups have 6 things in it, but they are decidedly different, right? Because order doesn't matter here, but order does matter here, right? Because if you multiply, if you go 1, 2, 1, 3, you get this. If you go 1, 3, 1, 2, you get that. So order does matter. Let's see what the subgroups look like. Let's start with this one. I'm thinking it might be easy. And let me list the cheapos for you. There's one of them. There's another. Right, those are the two extreme examples that I know I'm gonna get. Can anybody give me another subgroup, one that's not one of the extremes in Z6? Which one?
Even.
That works. Here's another one. There's actually one more. Let's see. Well, let's see. I think we can all agree both of these are subgroups, right? Because they're extreme. Why does his work? Notice that when you combine any two of these, it's still in group, right? 2 + 2 is 4, 4 + 2 is 0, 4 + 4 is 2, right? No problem there. It's got the identity, and everything's got an inverse, right? The inverse of 0 is itself, and these two are inverses of each other. So it's a subgroup. But thank you for that. Well, let's think about it. What happens if you have a subgroup that contains 1? If you have a subgroup that contains 1, it also needs to contain 1 + 1. Right? So now you got 2. And you got 2 and 1, so now you got 3. You got 3 and 1, now you got 4. Any subgroup that contains 1 is going to get everything. And we've already listed that, right? What happens if you have a subgroup that contains 5? Well, you can go through the same thing. If you got 5, and you got 5 + 5, which is 10, which is 4. And now you've got 5 + 4, which is 9, which is 3, 5 + 3, and so forth. And actually 5 is -1. I should have picked up on that. Right? Any subgroup that contains 1 or 5 will be everything. Yes.
0, 3.
Indeed. Very good. Everybody okay? Notice the order of this group is 6, right? What are the orders of the subgroups? How many elements are in there? This is very similar to that example we did last time about orders of the elements. Notice that the sizes of the subgroups divide the size of the group. This is not a coincidence. For this particular example, and the next one also, I will get a subgroup for every divisor of the group. That is a coincidence. That doesn't happen. What has to happen is the size of a subgroup divides the order of the group, but just because something divides it doesn't necessarily mean you have a subgroup. Okay, so here are the two silly groups here. Anybody see any others? This is a subgroup because these two are inverses of each other, right? And this times this is this, and this times this is that. So it's a little subgroup. Here's another one. That's almost silly as well, because notice this is its own inverse. This times this is the identity, so this is a little subgroup. But there shouldn't be anything special about 1, 2. Notice, for example, you can't have anything bigger either, because if you have a subgroup that contains 1, 2, and 1, 3, then you contain both of these two elements, and you can show from there that you get everything. Right? This one actually has a subgroup for 1, 6, 3, but now it has 3 subgroups of 1, 2, not just one like the last. Okay, any questions on it? Any questions? Okay. I'm gonna give you one last definition, because I want you to think about this, and I want you to think about where you've actually seen this before. You've seen one of these structure proving things before, or structure functions before. Definition. G circle and H star be groups. A homomorphism phi from G to H is a function. It's a function from G to H satisfying. It's not just any old function that goes from G to H. It respects the structure. Notice this is going on in G. So phi of whatever you get when you combine these two is the same thing as taking phi of G1, phi of G2, and putting them together over an H. We'll talk more about what this means next time. Any questions? Any questions? Okay, I will see you all